Yes.
Yes.
Thank you. So, it's not really this one. Uh, Rather, it is this one. So, before going to details, I didn't want you to leave this course without knowing what is a Frobenius number, which is very funny. So, suppose you have a large an unlimited amount of coins. So as many coins as you like, but there are only just two types of coins, A and B, say 5 cents and 7 cents. Seven because it's a strange country. And the question is, can you produce every desired amount using just A and B? Can you combine these two coins so as to get whatever you like? The answer is, of course, no. For in general, it is no, because, for instance, if A and B are both multiple of, say, 4, whatever, no matter you combine these two coins, the result will be always divisible by 4. So if you want an amount which is not divisible by 4, you cannot get this amount. So a necessary condition is that A and B, the values of the coin, are coprime, but even in this case, you cannot get whatever you like, because, for instance, if you pick A equal to 5 cents and B equal to 6 cents, you cannot get 4. Of course, you can get 4, but you must subtract. So it does not make sense to add a negative a negative number of times a coin. There is a related question. For instance, this one. Suppose you have a tank, a huge recipient, and you have two bottles, A and B. Say a bottle has A liters and bottle B has B liters, and then you're allowed to perform only two operations. You can fill and empty this big. You can take the bottle, you can put the bottle inside, and empty whatever you fill it so far. So using this fill empty operation, you're asked to answer this question: can you fill any tank of any capacity with A and B? Which are the conditions? What are the conditions on A and B that ensure that you can fill exactly the capacity of any such tank? So try to answer this question, which will be really easier after we think a little bit on Frobenius coin problem. So we were left with this observation. Although being coprime is a necessary condition on A and B to produce the desired amount, it's by no means sufficient, this condition, because you have a constraint. You have a constraint of the number of coins of state A and the number of coins of type B, these two numbers must be non-negative. So what Frobenius notices is that, however, there is a largest and maximum number which is not expressible as a linear integer combination of A and B with non-negative coefficient. Below this number you cannot express, but above these numbers you can express every number which is at least the Frobenius number plus 1 as a linear integer combination with positive non-negative coefficient, actually non-negative coefficient of A and B. For instance, let us write a little bit something. Here it is. So pick this one. So for instance, look, the numbers we are consider the coin, the value of the coin is 5 and 6. So 20, can you express 20 as a linear integer combination of 5 and 6 with positive coefficient, non-negative coefficient? Yes, you can, because 4 times 5 plus 0 times 6 is exactly 20, 21. 3 times 5 plus 1 times 6 is 21. And you can check that this work. This works for every number larger than 19. Does it work for 19? No, it doesn't, because 19 is actually the Frobenius number of 5 and 6. What is that's the Frobenius number of two positive integer A and B? Is the largest number which is not expressible as a Bezout identity, namely a linear integer combination with non-negative coefficient. What Frobenius actually proved is this formula that the Frobenius number is equal to the product of the two numbers minus their sum. For instance, in the case of 5 and 6, which is a very nice formula, in case of 5 and 6, you get exactly 19. So, what I want you to do is to prove the formula. Of course, we now discuss some hints about a strategy of proof, but it is quite instructive, rather instructive to prove this formula. So you must assume, we have seen this, we must assume that A and B are coprime. But if this is the case, then there is a Bezout identity expressing one as a linear combination, integer combination of A and B. One as a linear integer combination of A and B. This means that A and B can be of whichever sign. Of course, notice, since one is positive, A and B are positive. If S is positive, T must be negative. So it is readily seen that not both can have positive sign. However, now pick the number you want to express as a linear integer combination with, let us call this Frobenius combination, because it's not a Bezout combination, it's not a Bezout identity. So from the time being, from now on, a Frobenius combination is just a linear integer combination with a non-negative coefficient. So pick a natural number n that you want to express as by a Frobenius combination. Since you have the Bezout identity here, just multiply both sides by n to get this expression. So, and actually you have expressed n as a linear integer combination of A and B. It's not yet a Frobenius combination, but it is a Bezout combination. Now, here it is the trick. Divide. So one of the two is positive, is non-negative, and in particular it's positive. Of the two coefficients, one of the two is positive. Let's say this is positive, and so divide Sn by B. It doesn't change too much if Sn were negative. We defined the Euclidean division for arbitrary integer number. So the only condition we which are interested in is that the remainder of the division satisfies this condition, which is granted by the property of the Euclidean division. So divide Sn by B, and you get the quotient and a remainder as usual. So now express R as the difference between Sn and QB. Do the simple computation here, and you get that n can be expressed as a linear integer combination with coefficient of special form. The coefficient of A is non-negative and is not greater than B. We don't have control on the coefficient of B. However, so far we proved that every positive integer n can be expressed as a linear integer combination of two coprime numbers A and B, where the coefficient of A is non-negative. It is bounded above by B minus 1. This is a very general. Using this representation, we can solve the Frobenius coin problem, because we are looking for the largest integer n with the property that is not expressible as a linear integer combination, as a Frobenius combination. Now, but every integer number n can be expressed as a Bezout combination where the coefficient of A is non-negative and bounded. So if n is not expressible, since R is non-negative and bounded by B minus 1, the only possibility is that X is negative. Otherwise, we would have got the desired Frobenius combination. So we are looking for the largest one, which fails, which misses the condition, which violates the condition. So n is the largest one, which is not expressible as a linear integer combination, as a Frobenius combination. So since any such combination as its Fields coefficient in any such combination, the Fields coefficient can be chosen non-negative and bounded by b minus 1, the only possibility is that x is negative. But we are looking for the largest one number expressible in this way, which is not which qualifies for the Frobenius problem. So the maximum n, which can be expressed by r times a plus x times b, where r is non-negative and x is negative. So I let you complete the exercise because this maximum is rather easy to find. Just observe as a hint that, of course, since x is negative, the bigger is b, the smaller is n. It is clear. It is decreasing with b, this expression, not with b, with x, sorry, with x, this expression, because x is negative, b is fixed. So since x is negative, the larger is x, the smaller is n, of course. And the larger is r, the larger is n. So it the best thing to do is to pick x as the minimum at its minimum possible value, which is -1, of course, and r as its maximum possible value, which is b minus 1. So if you, with these two choices, if you do the easy computation, you get exactly, precisely Frobenius formula. So this is your homework, and let us come back to our hot topic, which are congruences, linear congruences over the integers. So we started to look at this new relation. We saw several things about congruences, and we observed that we can play with these residual classes modulo n as if they were numbers, because on what time recalling you now. So as more recap, so recall that A is congruent to B modulo n if the difference is a multiple of n. Recall that the class of A modulo n is the set of integers which are congruent to A modulo n, and they are all of this form. These are these cosets, these lateral classes. And of course, among the integers equivalent modulo n, congruent modulo n to A, there is a smallest positive one, which is R. What is R is precisely the remainder of the Euclidean division of A by n. So every integer is always congruent modulo n to the remainder of the division of the integer by n. Then we observed that since the possible remainders of a division by n are n from 0 up to n minus 1, and so there are exactly n equivalence classes, congruencies classes of an integer modulo n for an integer n. Every positive, non-negative integer n induces, we say that induces, yields exactly n residual classes modulo n. So what I'm thinking is, so maybe we missed it to observe this fact. So what is, does it make sense to consider minus n? It is different from z modulo n. If you think a little bit on, you see that is not just just consider the definition. And so the exercises that I give from scratch now online are this following one. Does it make sense Z0? And if yes, what is Z0 and what is Z1? So what does it mean that two integers are congruent to each other modulo 1? When they are congruent to each other modulo 1? And when are congruent to each other modulo 0? Think a little bit on. I leave you this as an exercise. Good. So, what we did with this quotient by the congruence relation. So recall that the set of equivalent classes with respect to an equivalence relation is called the modulo of the set with respect to that relation. So we are working on zeta with the equivalent relation, which is congruence. The equivalence classes are called congruence classes, but it's still a quotient, a special quotient. And we introduce operation, binary operation, on this set. So what we observed is that though these objects are not numbers, they are sets, we can anyway define an addition and a multiplication so that the commutativity, the associativity, commutativity, and distributivity property are fulfilled by this operation. They also have neutral elements with respect to addition and multiplication respectively. The neutral element being 0 for the addition, being the class of 1 for the multiplication. So 0 is the class of n or the class of 0 of the class of 5 times n. It doesn't matter. It is called the representative, the whatever you put within the square brackets here to denote the classes, because the class does not depend on the representative you choose. You can put 1, you can put n plus 1, you can put 2 twice n plus 1, 3 times n plus 1, whatever, or also n minus 1, why not? Well, sorry, 1 minus n, which is minus n minus 1, within brackets. So, and we define these rules for the addition and the multiplication. So we, to add to class, we just pick an arbitrary representative of the first class, an arbitrary representative of the second class. We perform the sum in zeta, and then we take the class that this sum represents. So, in other words, and shortly, the sum of two classes is the class of the sum, and the product of two classes is the class of the product. So here, using these two sides of the channel of the identity, which is now an identity because even we didn't check that this is a well-defined operation. It is an operation, so we can assume that this is a definition, proper definition. So if you look at these two sides, they also give you somehow operative rules, because for instance, you know how to you know how to compute from I don't know for instance, if you want the product of the modulo 10 of the classes 3 and 5, this side of the chain tells you that you just have to reduce their product modulo 10, and so for the sum is for the addition is the same. On the other hand, if you move on the last side, this one or this one, here you don't have a rule, but you had written in advance the Cayley table of the arithmetic. So just here, these two symbols are not related with actually their meaning, but are just symbols, and you read on the table the corresponding entry, or the multiplication table the same. So just two different interpretation with the same meaning, because the Cayley table, you build the Cayley table by means of these rules. We observe that this is actually an arithmetic, because we already mentioned that the operations enjoy whatever we like, the important properties of the integer and of the integer addition and multiplication, and also this may have escaped your attention. Also, we have this rule, which is iterated multiplication, which is the operation to rise into the power, and it behaves exactly as the product behaves. So the only thing missing to have the complete picture is to find, which is the most important, the most important object to know, the multiplicative inverse of an element of a class. But however, we already observed that this multiplicative inverse may not exist. For instance, I think you did some practice on your own, but you cannot invert to modulo 4. So there is no A which gives 1 modulo 4. This so there are conditions ensuring that the inverse of an element exists modulo n. They are very easy. We are looking at this. Sorry, we are looking at this condition in a while. But what is important? Let me stress once again that working with symbolically with and this strange object provided that you know the Cayley tables of the arithmetic, or working with these congruence modulo n is exactly the same thing. There are just two interpretations. This is more useful when you look at a geometrical property of these classes. For instance, in group theory, we are interested in in abstract, say, symmetries rather than doing computation. So, but they are exactly the same thing. Indeed, say, just writing these rules is equivalent to say that if you pick A congruent to C modulo n and B congruent to D modulo n, so the sum A plus B is congruent to the same C plus D. This proves that I don't know, I think it's antonomasia, also antonomasia, also in English, I don't know, but this is the prototype of a general congruence. So you have a set, you define, you have a set, you have a quotient with respect to a given equivalence relation, for instance, congruence. You define operation on the classes, and you have to check these. And when this is true, when you are given a definition of sum and multiplication of another operation that you may like, and you check that this operation does not depend on the particular representative chosen, then you have an algebraic structure built on the quotient. So this is a very, very general fact in algebra. And this also for more abstract notions, for instance, for symmetries, permutation, for just one an operation in most cases, but it is really the same thing. It is really the same concept. Now, the last thing we have to treat before discussing a little bit more intriguing questions like the main idea of RSA in cryptography. We need just to solve this question about the inverse, about the existence of an inverse of an element modulo n. So it is really, really, really easy, and we saw it several times, and it is always the same things, and still depends on the Bezout identity, which in case two numbers are co-prime, express the two numbers as a linear integer combination. The two numbers are as a linear integer combination, which equals to 1. Which equals 1. So, what is an inverse modulo n of an element A? It is just so what is the inverse in the set of real numbers of A, or we already saw this, but what is the inverse of a real number A in R? So the condition is this, that R, that A is not 0, because otherwise it is not invertible straightforwardly. So if A is different from 0, the inverse of A is the unique number B such that this relation is satisfied. So we also say that the unicity of B allows us to write the inverse, to denote the inverse by the symbol A minus 1. This is not an operation. This is just the way to call B. Since B is unique for A, it depends only on A, rather than call it B and writing every time this chain of equalities. We denote the inverse by A minus 1. So it is just a symbol, which is also denoted as the reciprocal in this way, 1 over A, which is another symbol, which is this symbol. Good, is another symbol. So we know using the definition which meaning we have to attribute to this symbol, and so we know how to compute this symbol, but these are symbols, not operations. Good. So in Zn or modulo n is actually the same things. The inverse of A modulo n is the unique modulo n. Unique modulo n means that of course, there can be two different integers satisfying this equation modulo n, but they are in the same class. They are pairwise congruent modulo n. This means unique modulo n. It doesn't mean that there is exactly one. It means that if there are two, they differ by a multiple of n. So this is the definition. Ax congruent to 1 modulo n is the definition of inverse of A, provided this inverse exists, because it may not exist. But when does the inverse exist? Whenever A, the class we want to invert, and the modulo are coprime. So Ax congruent to 1 modulo n as a solution, if and only if the coefficient and the modulo are coprime. In that case, the inverse exists, and such an inverse is unique modulo n. Look, it's really trivial. It's really trivial. Just follow the flow and the definition. So what does it mean, Ax congruent to 1 modulo n? It means that Ax minus 1 is congruent to 0 modulo n, of course. But what does it mean that A times x minus 1 is congruent to 0 modulo n? That the left-hand side is a multiple of n. That is, that n divides Ax minus 1, which means that there exists an integer q such that qn is equal to Ax minus 1, which means that we are here now. Sorry. We are looking and these steps. So these are, of course, equivalent. And if what is this? What is this relation? It's just a Bezout identity expressing one as a linear integer combination of A and n. So if we found a linear integer combination expressing one as in terms of A and n, we concluded that A and n are coprime. So these are all equivalents. You can reverse the flow. You start with two coprime numbers. This is true. There is a Bezout identity expressing one in terms of A and n. Put transport on the other side, the multiple of n, and then apply slavishly as a robot the definition, and you get the results the other way around. So this is what we have to know this is the basic step to understand the way RSA cryptography works. And just here a few stupid, really silly and stupid examples. For instance, since 2 times 3 is congruent to 1 modulo 5, it means that the inverse of 2 modulo 5 is 3, and conversely that the inverse of 3 modulo 5 is 2. It's unique modulo 5 in the sense that 8 is still satisfies this 2 times 8 is still congruent. So 8 is also an arithmetic inverse of 2, but is the same as 3 modulo n. Indeed, 8 and 3 are in the same class modulo 5. So you can argue in this way. So let us look at the inverse of 3 modulo 5. Clearly, 2 plus any multiple of 5 clearly satisfies the congruence. However, to this number and 2 are in the same class modulo 5. Expressing the inverse in Zn this times is meaningful because it is really unique. It is the only, because the element of Zn is the class, you are not distinguishing between the representatives, but you are taking the classes as a whole. So the inverse of 2 in Z5 is 3 and is unique. There is no other symbols within Zn which satisfies 2 times 3 equal, not congruent to 1 in Z5. This is inequality this time. It's not a it's no longer a congruence. So, however, the meaning is the same. So here you treat as a whole the entire class, and here you work with the representatives. The only difference is this one. So let us apply what, oh, maybe it's time to pause a little bit, and then we continue with this example, this other. So there are several things to do still, but we are a good point. We are a good point. Yes. So I stop for a while. I hope you do. You do as well. So see you in 5, 8, 10 minutes. See you.
Hi.
to see you again. I hope you record a bit. So we now go on on what we left. So we are talking about congruences, modulo n. We saw several properties of the congruences. Also, we showed as to use the defining operation of sum and product or multiplication more precisely. We also explained how to find a multiplicative inverse modulo n of a given element, and we also make bridge between congruencies and the congruencies classes of the congruence relation, and we saw that sometimes it's better to work with congruencies and some other time is better to work with Z and with the classes as a whole, but in any case they are the same thing. So let us exploit somehow what we learned to solve some easy exercise. So look, this may look difficult to solve. So 23 raised to the power of 1931, and so you are asked to find the remainder of the division by 4 of this huge number. So how to cope with this problem? Just find, since the remainder of the division by 4 is just the congruence class modulo 4 of this number, we just look for this class. And applying whatever we know about these classes. So the first thing to notice is that 23 is so large without any utility, so we can reduce it modulo 4. 23 is congruent to 3 modulo 4, so this class is the same as this class. So now we are stuck because what can we do? We can try to raise 3 to this huge power, and then taking the class modulo 4, or which is the same thing as raising to this huge power the entire class modulo 4. But this is useless. We don't get anywhere in this way. Better this way. So look, 23 is 3 modulo 4, but is also minus 1 modulo 4, and now it is because minus 1 rises to a not power is minus 1. So this huge number is the same as this number, which is the same as this number, and so its class is the class of minus 1 modulo 4, which is the class of minus 1 plus 4 modulo 4, which is the class of minus 3. So, and this is something that you must remember. Since 3 is smaller than 4, it is exactly the remainder of the division. So since this class always contains the division, the remainder of the division, the smallest positive representative of the class is the remainder of the division modulo 4, we have found exactly this remainder because the representative is smaller than the modulo. So the remainder of the definition of the division by 4 of this huge number is just 3. Good. Now, something that probably all of you knows, the proof by 9. So if you want, so this is really easy. It is really easy to prove this divisibility criterion. So a number is divisible by 9 if so are the sum of its digits in the unique decimal expansion of the number. So maybe this can be done in some details. It is very so you have A expressed as say 4 digits, then you can easily generalize. These are the 4 digits. So A, this is another way of saying that A is x3 times 10 times 1000, of course, x2 times 100, x1 times 10, and x0, you can avoid to write the 0th power of 10, which is 1. So now, what we learned is that by the sum multiplication rules, the class of A modulo 9 is the same as the class of each term modulo 9. Okay, can we ignore the can we ignore the PADEX 9 here because it's rather tedious to write it down anyway. So, good. Let me write for the last time. Then I can neglect the PADEX 9. So again, since the class of the product is the product of the classes, we can write very slavishly. So then, this is the power of algebra. Once you have understood something, you can forget. So last step, the class of a power is the power of the class. Now, this is the only start to understand, since we are working modulo 9, oh, modulo 9, sorry, since we are working modulo 9, each digit is a number which is between 0 and 9, so it is exactly the remainder of the division by 9. So we, in a sense, we could ignore these brackets, this class. Now, then the class is 1. Of 10 is 1. Rise to the third power is still 1. X2 rise to the second to the square is still 1. Oh, sorry. I think I missed. No, everything is plus 1 plus x0, which is the same as saying let me, otherwise is not precise. The plus x2 plus x1 plus is 0. So picking the leftmost hand side and the rightmost hand side, you see that this equality means that A is congruent to x3 plus x2 plus x1 plus x0 modulo 9. So what is the proof by 9? It's simple, the definition of multiplication by classes. The proof by 9 is just this. Nothing more, nothing less. It's just the definition of product of two classes, modulo 9, modulo n, of course. So what you do in the proof by 9, to check whether the result of the multiplication is right, you check whether it is right modulo 9. This is proof by 9. Indeed, you put here A reduced modulo 9. You put here B reduced modulo 9. You put here AB reduced, no, sorry, yes, no, put the other one. Here put the product of the classes modulo 9, and here put the result modulo 9. This is the proof by 9. Also, look, suppose you have a long decimal expansion, for instance, 1387222, you can permute anyhow as you like the digit of the representation, and you get the sum result modulo 9. This is something with a kind of joke. I saw it several times. People that say, "Oh, this magic, write 1, 2, 3 up to 9, and then pick in the reverse order." And I don't remember which property, but the properties, of course, that they are congruent each other, these two different numbers induced by different permutation to each other modulo 9, because the sum is the same. because the sum of the digits is invariant under permutation. This is the reason. Also, this is completely up to you. Just the definition of n factorial is n factorial is just the product of all integers between 1 and n. So, for instance, 3 factorial is easy. Is 1 plus 2 plus 3 is 6. And so 4 factorial is 24. And 5 factorial is 120. So the exercise asks you to find the class modulo 4 of n factorial as n ranges over the natural number. So you have to say which is the general form of this class. It's easy. It's not difficult. And the other one is to compute the remainder modulo 4, which is the same as the residual class modulo 4, which is the same as the class modulo 4, which is the same as the element of zeta 4 represented by this, whatever you like, of the number 1 factorial, which is 1, plus 2 factorial, which is 2, plus 3 factorial, which is 6, plus until 30 factorial. So this is completely up to you, and I think you experienced a little bit the beauty of this kind of operation. So you can look, however, to other exercise. For instance, you can explore by yourself all the divisibility criteria that you know. For instance, divisibility by 3 or divisibility by 11. So this is nice. For instance, pick the decimal expansion, just three digits. Working modulo. No, this does not make sense. It is a x2, x1, x0, and we look at the class modulo 11 of A, which is the class modulo 11 of x 100 plus x1 and plus x0, which is as before, as x0, which is minus 1 plus no, which is 1. This is minus 1, and this is 1. So here you take the sum with alternating sign and divisibility by 11. So A is divisible, 11 divides A if and only if the class of A is the class of 0 modulo 11, or even if A is congruent to 0. modulo 11, and this happens if and only if the alternating sum of the digits of A in any decimal, in the unique decimal expansion, since they are integers, it is unique, it is equal to 0. So, for instance, 121 is divisible by 11 exactly because 1 minus 2 plus 1 is equal to 0. Good. So you can do several things. So up to this level, it seems to be rather a recreational mathematics or something that you can use to surprise your friends or something like that. However, and here it comes, the very powerfulness of all this stuff, you can use also for doing algebra at a very high level. You can use in a very practical application, which is cryptography, which is also the subject of this course. So, last things to know, it's the main idea of the RSA cryptography, which is also public key cryptography, and acronym RSA is not mysterious. It's just the it's just the string formed by the second names of the authors of the algorithm, Rivers, Shamir, Adelman. But the idea, it's surprisingly simple. In Italian, we say the Columbus egg. Is so easy that we can do it in 20 minutes starting by now. The implementation, writing a code, finding the primes, this is not trivial, but is a computer scientist question. The mathematics is really, really easy. The mathematics is really, really easy. So we need the notion of Euler-Phi function, which is one of the most important arithmetic function. So how is defined phi? In the first place, phi is a function, so and it is an arithmetic function, so its domain, the set where it takes values is the where it takes arguments is the set of natural numbers, and the image is codomain. The image, not necessarily the codomain, are natural numbers because it is defined in this way. Pick any natural number, so not any natural number is any natural numbers at least one, and its value by phi is exactly the number of integers which are equal or below n, with the additional property of being coprime with n. So, some examples. P1, the greatest common divisor of 1 and 1 is 1. 1 is at least 1, so Phi1 is 1. Phi2, let us look at Phi5 before Phi5. So the rule is pick 5 list all integer which are not greater than 5, and then delete from the list those which are not coprime with 5. So it is only 5. What is left is exactly the set of prime which are not larger than 5, which are coprimes with 5 or 6. Write 1, 2, 3, 4, 5, 6, and delete everything is not coprime with 6. So 2 is not coprime, 3 is not coprime, 4 is not coprime, 6 is of course not coprime, so it remains only 1 and 5. This implies that phi d6 is equal to 2, while phi d5 is equal to 4. So do you see? It's not monotone. The function sometimes may be high, sometimes may be low, and but we know how it behaves on particular numbers, this function, when this is obvious by the definition. If n is prime, then phi dn is exactly n minus 1. Why? Because all the integers which are not greater than n are coprime with n because n is prime. So this is the definition of prime. It has no proper divisor other than 1 and itself. So you must delete only the last from the list. So phi d7 is equal to the cardinality of 1, 2, 3 until 6, which is 6. Now, this is a trivial fact. It follows straightforwardly by the definition. A little bit harder, but still easy fact is the following rule. So for a prime, it is easy, but what is phi for the powers of a prime? So pick, for instance, phi p rises to h power. Here it is the value of phi in p rises to the h, which can be written if you group by ph minus 1, can be written in this way, which is the usual way in which it is presented. But this is not only equivalent, it is already the proof that this is exactly that the value of phi in p to the h must be this one. Why? It's a very simple proof. So this is the way we presented the phi function. We listed all the integer which are equal or below n, and then we delete those which are not coprime with that. So what is phi dn is the number of integers which are equal or below n, which are not coprime with n. So we first list those which are equal or below the given number, then we'll delete something. So what is the number of integers which are below or equal to p to the h. Of course, it is pH. No? Just list all the number. Exactly in the same way, the number of integer m which are not greater than a is equal to a, exactly in the same way. You list one by one and you get pH as the cardinality of this set. Sorry, guys. So we have to delete something from this set. What are we deleting? Those which are not coprime with P, but P is prime, so there is a unique possibility to have number which are not coprime with pH. There must be multiple of P. There are no other possibility because pH, the divisor of pH are only P and their smaller power. So, which is the number of integer which are not greater than P to the H and are multiple of P is exactly this set. Written in this way. The set of A such that A times P is not larger than PH. And how many are these? They are exactly P to the H minus 1. Why? Just right. Just right. Start with P, 1P, 2P, P minus 1P, and then you get P to the square. Because you multiplied P times P. And these are the first P. And then P squared, 2 times P squared, 3 times P squared, until, sorry, sorry. This is barely right. This is not in this way. This is in this way. However, just this is P squared. And so you get P to the third power, so 2 times P to the third power, and so on and so forth. So they are exactly P raised to the power H minus 1. And so we have to remove from the first set the element of the second set, the element of the first set are P to the H, the element of the second set are P to the H minus 1, so their difference is exactly this one. And this explains why this is the form of P evaluated in a power of a prime. Here, this is the most important fact, which says that the phi function is multiplicative, is an arithmetic function, multiplicative, is that the product, the phi of the product of two primes is the product of the phi of the two primes. So this is equivalent to the so-called Chinese remainder theorem. This is exactly the Chinese remainder theorem. It's not difficult to prove, but it is not immediate, so we don't have time to prove this. But now we have another easy fact that combines phi, this rule, phi into the power of a prime with the multiplicativity of phi, and which allows to apply to evaluate phi at every natural number because of the fundamental theorem, unit factorization theorem, fundamental theorem of the arithmetic, which asserts, I recall you this, that every natural number can be written uniquely up to the order of the factor of powers of prime. So you apply the multiplicativity and you uh, evaluate phi at the power of primes, first apply multiplicativity, and then the rule to evaluate phi at the power of prime, and you get exactly this. Now you can divide, you can group by PE, PI in each of the factor, and it is easy to see that you get. This is just a matter of computation that you get this expression. Phi dn is n times this product, the product of 1 minus the reciprocal of the divisors of n. So here are some experiments, physics. You can apply this definition, and so you get phi 2 is prime, so is 1. 3 is prime, so is 2. It is the product is 2. Or you can apply this definition and you pick 6. The divisor of 6 are 2 and 3. You write 6 times 1 minus 1/3 times 1 minus 1/2, and you get exactly the same result, which is 2. Better 340 because 100 times 1/2 times 1 minus 1 over 50 is 100. 1 over 2 times 4 over 5, so is 100 times 2 over 5, which is 200 over 5, which is 40. Or you can use the fact that 100 that 100 is 2 squared times 5 squared, and you can apply this rule so as to get by multiplicativity you get this, then apply the rule which says 2 times 2 minus 1 times 5 minus 1, which is 2 times 4 times 5, which is, of course, 40, as it should be. Good. We are almost done. Here it is the most important consequence of what we see. It is very, very nice formula with generalized called Fermat little theorem, which says that anytime you pick two integers a and n, a is coprime to n, so a rise to p n is congruent to 1 modulo n, which is very, 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 very nice. And the trivial consequence is that you have immediately a way to compute the inverse of A even for very, very, very huge number. So, for instance, to appreciate, suppose you pick 5 to 1 plus 7 plus times 1, 2, 3, 4, 7, 0, 0, 0, 0, 8, 9. Yes, you can pick. I don't know what is 6 times this number, neither what is 6 times this number plus 1, but 6 is of 7. So what I can say immediately is that plus this, call this huge, plus huge is congruent to 5 modulo 7. Yeah, I can immediately say that. So you can, if in, of course, 5 and 7 are coprime, so we can apply Euler's theorem. So, but look, it's extremely powerful because here can be really, really, really huge, this number. No matter how huge this number is, this power depends only on the remainder of the division of the sum of these two numbers, one divided by PDI. Probably it's better to do a smaller example. For instance, let me think. 5 to the power 21 is congruent to the third power modulo 7, which is also congruent to minus 2 t power modulo 7, which is also 2 alla 3 to rise to the third power modulo 7, which is also 1 modulo 7. But also 6 is congruent. Actually, this is the most important ingredient in the RSA algorithm. This is the most important. So I wanted to show you the proof of Euler's theorem, but I'm not sure we have enough time. Let me describe first the RSA algorithm. The statement of Euler's theorem is clear. It is this very, very, very nice form, nice equation. Oh, sorry. Which reduces to AP minus 1, this is Fermat's little theorem. This one. Provided the A is not a multiple of P, otherwise you can put it in this way, which is the same. And this also for A, which is multiple of P, as you see, If A is a multiple of P, then they are both divisible by P, so they are congruent to 0 modulo P, and so this is 0 congruent to 0 modulo P. If A is not multiple of P, since P is a prime, A is coprime with P, and so this holds as a special case of Euler's theorem. However, it is oldest it came before that Euler's Fermat's little theorem. So this is clearly a special case of Euler's theorem when n is a prime, because phi n is exactly n minus 1 or p minus 1 if you use p instead of n, which we will see probably. And so is not too I want, well, good. So let me describe what is the RSA algorithm. So your goal, your aim is to encrypt a message and to send it to a friend of yours, maybe, and so you send it transparently over the internet, for instance, and everybody can see, but nobody can decrypt unless you don't have the key. So you need two keys to encrypt and decrypt. The one is the public key, is denoted by E, and the other is the private key, which is denoted by D. Now, what do you need to make the encryption and the decryption? You need a huge number n, very huge, because it must be difficult to guess. And this number should be should result from the product of two primes, which are themselves huge. They are large primes. So who tell us these numbers? Codes, prime generators. And we probably already your mobile has prime generators. However, choose these huge two primes, multiply then to get this huge number n. This is the first step. Then n is a product of primes, so we can easily compute, knowing the primes, the phi of n, which is exactly the product p minus 1 u minus 1, because by the multiplicativity of the phi. We know that phi of pq is phi of p times phi of q, which is p minus 1. This is q minus 1. Good. Now fix the public key. The public key is just an integer, not too large, but surely smaller than phi dn. It must be smaller than phi dn, because we want to compute the class modulo phi dn. So if it is smaller of phi dn, we know the E, the residue of E modulo phi dn is exactly E. That's why we need that E is smaller than phi dn. So this is the public key. What is the private key? It's just an inverse, a small inverse, let's say, we saw there are several, say the smallest inverse of A modulo phi n, that is the inverse of A in phi n. Good. So if it is an inverse, it satisfies the following relation. Good. Now, suppose you want to send this message M. M can be huge itself, but it cannot be too huge. It must be it must be not larger than phi d, but it can be huge. So you want to encrypt M. What do? Just raise M to the power of E to the public key to get C. And everything is transparent here. Everybody can see this. You pick M, you encrypt, you send C. C is encrypted. How, when you get C, when you receive C, to decrypt it, you just raise C to the power of D, the private key, and this only you are the owner of the private key, nobody else, unless you, you want to tell others your private key, but it's yours. So why it works? Why C to the rise to D is the decryption of the message? Because of this relation. So we are going to show that CD is equal to N. You restored the original message. It's really easy. So C rise to D is by definition M to the E rises to D by the power rules. It is M rises to E times D. But because of this relation, because A, D are inverse of each other modulo phi n, this is true. It is true that AD is equal 1 plus K to times phi n. This is saying that AD solve this congruence, or saying that AD is 1 plus a multiple of phi n, sorry, is exactly the same thing. This is the definition of congruence, modulo n, in this case, modulo phi n. It is exactly the same thing. So from here, we get that M is raised to 1 plus K times a multiple of phi n. By the rule of powers, you can write this as M times N raised to the multiple K of phi n, but the multiple K of phi n by the rule of powers is just M raised to phi n raised to K, but this is U by U0 exactly the same. Which is exactly what we had to do. So we have, so maybe this is more, sorry, this is So sorry. This should be N, no more, not V N. Otherwise, it doesn't work. So where I got wrong? Encrypted. It must be. No. This is modulo N. This is modulo N, of course, and the request is that M is smaller than N, which is huge. So you have enough space to encrypt the message. So sorry for this. Everything is right till this point. So from now on, you are working modulo N, and also this one. Also this one is so. Also this one is modulo N, but since, sorry guys, but since, no, not that, but since M, sorry, right, strictly smaller than N, and this is the last flow is this. Oh, we got it. So let me recap just everything goes well except for the last 3 steps, where instead of using, as I mistakenly wrote, Pn, we have to use N, big N. So you choose a message N which is smaller than N is an integer smaller than this huge input integer and big N. You raise N to the public key to get a message C, encrypt. You send it transparently. Then to decrypt, you just raise C to the private key that only you know. And the observation is that C raised to D is exactly M. To prove this, it's sufficient to prove that this holds modulo N, because in this case, M would be the residual modulo N of M, which is M itself, because M is less than, is strictly less than big N. So there are simple steps. You write CD as M raised to 8 times D, and test D can be written because of the choice of A and D, so as to satisfy. This is modulo of N. This is modulo of N is the only place which we take the modulo of N. So using the definition of A and D, which satisfy the congruence AD congruent to 1 modulo phi n, we get that M to the 8 times D is M to 1 plus a multiple of phi n. And we observe that M times a multiple of phi n is equal to M times M to phi n to K, which is congruent to 1, this within brackets congruent to 1 modulo N because of Euler's theorem, and therefore, in conclusion, C to the private key is equal to M modulo N, but since M is smaller than big N, its residue is exactly M, we are done. So since this old modulo N, but since M is smaller than N, it also without the modulo. So this is this, just to clarify. So if I ask you to compute 5 modulo 4, sorry, if I ask you to compute 7 modulo 4, you get 3 modulo 4. And so the canonical representative, that is the smallest integer in the class, is different from the chosen representative. But if I choose, instead of 7, 3 modulo 4, I get that the smallest representative in this class is exactly what is written here. So if this holds modulo n, it is also without the modulo. This is RSA. We started with natural number Peano axioms. We went through several notions in elementary higher algebra, and we ended up with this very, very elegant, simple, but powerful algorithm for encryption, which is the strength of this algorithm. And you cannot violate the private key unless I don't tell you which this private key is, because the factorization, of course, if you knew P and Q, you would have done, because the knowledge of P and Q allows you to know phi dn. And if you know the public key and the modulus phi n, you know also its inverse, which is D, and you can decrypt the message. So knowing E, but not knowing P and Q, does not allow you to know D with your private key. To know D, you must factorize N. That is, you have find primes P and Q whose product is Z. And this is a very difficult problem, especially from a computer science point of view. So that's why RSA works. Good. I hope, sorry for the delay. I hope you enjoyed this lecture so far, and I'm sure you will enjoy more practical lectures coming with Paolo Franciosa and Fabrizio De More. So see you. Best to you, and see you next time, even I don't know when. Ciao, ciao.
Bye.
Bye.
Ciao.